Hello again, my dear students. Now, this is the part number 2, the final part with our lecture number 5, dealing with signal digitalization or converting analog messages into digital. In the previous part, my dear students, we have discussed together the journey of the sampling, which is the process of discretizing the time domain or the time axis. As we remember from part number 1, that this is a semi-digitalized signal because in order to have a digitalized signal, you should have a discrete time axis and a discrete amplitude axis. So in this lecture, or in this part specifically, we are going to illustrate the process of discretizing the amplitude axis or the y-axis in order to have a complete digital signal, and then how we can encode or transfer this signal to be a binary format, ones and zeros, and different types of formats that can be used in order to do such encoding. So please accept my invitation to share now my presentation slides and start part number 2 of session. Okay, so I believe now you can see my presentation slides, and let's now start our journey as usual. We start with a very brief flashback on what we have already learned in part number 1 in our lecture, and then we go into the new content of this part. So basically, we define the difference between the analog communication signal or the analog communication system and the digital communication system in the terms of the message. In the analog communication system, we have an analog message, while in the digital communication system, we should digitalize the message through an analog to digital transformer before doing the modulation process. And here the modulation will be named as a digital modulation process. So in our current lecture, we are focusing on this block, how we can convert the analog into a digital signal. In order to do this task, we have to do 3 steps. The first is to discretize the signal from its time perspective or from the x-axis perspective, and this is what's called sampling. And then we should discretize the signal from the amplitude perspective, and this is what's called quantization. And finally, we should transfer this digitalized signal into some sort of bits or ones and zeros, and this is what we call encoding. So this is the full 3 processes of converting an analog signal into a digital signal. Now we start with the sampling process. The sampling is the discretization in the time domain. So as you can see here, the dotted line represents the analog signal. However, these weighted delta Dirac functions represent the discrete samples. In order to perform this process, we found that this is ideally to multiply the analog signal with a train of impulses, so you can get a discrete. I'm sorry here. So you can get a discrete values. Now I'm multiplying this time domain signal with a train of impulses. Then we get this weighted samples representing the original signal. We define the time interval between each 2 delta Dirac function as the sampling time, or the TS. And we found that, fortunately, the Fourier transform for this delta train of impulses is also a train of impulses, but with different spacing. Now the spacing here is called Fs, or the sampling frequency. The sampling frequency is actually the reciprocal of the sampling time. So whenever you have a narrower time in the sampling, I mean, whenever you decrease the sampling time, this region or the sampling frequency increase. This is a reciprocal domain. And then the multiplication process in the time domain will be represented by convolution process in the frequency domain, and then you can get this different types or different versions of the sound. Okay. Based on that, also we have also concluded, if you remember, the Nyquist rate or the Nyquist sampling rate, which is Fs, should be greater than or equal to Fm to avoid what's called overlapping, or what we name, if you remember, aliasing. Then we turn to realize the sampling process. What I mean by realizing it or transferring it into reality is that it's impossible to have this hypothetical train of impulses of delta-Dirac function, because mathematically a delta-Dirac function is an impulse with a width which tends to 0. And physically or practically, it's impossible to have a square wave or an impulse, both have the same meaning actually, with a width equals to 0. So this signal is an hypothetical signal. It's not a practically generated signal. So what we can practically generate is a train of impulses with a finite width. Let's call it tau, for example. This tau is small but not equal to 0. So now this is what we call the natural sampling. And by doing this, we have also recognized that the Fourier transform of this finite width impulses is a weighted sinc function, a discrete weighted sinc function, as you can see. And also we prove it in the previous lecture. Another type, which is what's called the Flattop. Actually, the main difference between the natural sampling and the Flattop sampling is that in the natural sampling, that the height or the amplitude of the impulse takes the shape of the message, as you can see here. However, here it was called the Flattop, or in other literature, it's called the sample and hold. You hold the value of the sample, as you can see, and then you maintain it during the duration of the pulse. And also, we have also discussed the Fourier transform for this time. Finally, we go to what's called the aliasing problem, where when the sampling frequency is relatively low, so we have what's called an overlapping in the spectrum. This overlapping in the spectrum destroys the baseband signal. The baseband signal is very important because this is the recovery signal. We know to recover back the signal because, as we discussed in the previous lecture, each step implemented in the transmitter should have a reverse step in the receiver. So in order to recover back the original signal, you have to use a low-pass filter, and then you have to maintain this baseband signal clean. So this is what's called the aliasing effect. And in order to avoid the aliasing effect, we use this anti-aliasing low-pass filter just before the sampling stage. So this is finally the process. This is finally the sampling process. Now in the new content of this part, we will start talking about the other two steps, the quantization and the encoding. As I just mentioned, in order to digitalize a signal, you have to discretize the x-axis, which is the time, and the y-axis, which is the amplitude. In the sampling process, we already have the first step, the discretization of the x-axis or the time axis. Now it's time to transfer back to the y-axis. So please consider that in the sampling process, if you avoid the aliasing using the anti-aliasing effect, you are capable of recovering back or restoring back the original signal without any sort of losses. So it's 100% recovering stage. And what I mean that you did you did some sort of sampling. So what you have now is something like that. Then you do quantization, encoding, transmission. Now the receiver, whenever the receiver has this sample, it is capable to restore it back to this, as far as you are avoiding the anti-aliasing effect. Oh, sorry, it's the aliasing effect by using anti-aliasing filter, and by also ensuring that your frequency or your sampling frequency, I mean, is greater than double the baseband frequency event. So now it's a recoverable process. What about the quantization? Okay, the quantization process simply, as I mentioned, is a discretization in the y-axis. So what we are going to do is that we are going to limit the values on the y-axis to a certain levels, and what is between these levels should be approximated either to the lower level or to the higher level. So In order to make it somehow clear, let's do some paper-based example. So please now permit me to stop sharing the presentation and to go to my white paper. Okay, so I believe now you can see it. It's perfect. Let's run a new pen. Okay, so let's assume, for example, that we have any signal like that. This is an analog signal. Why this is an analog signal? Because actually it accepts all values on the time axis. So for any time you have a corresponding value, and for any one you have a corresponding value. So let's assume, for example, that this is, for example, 1 volt, and this is, for example, 3, and we have also in between 2. Okay, so generally this signal accepts, this signal accepts any analog value between 1 and 3. The dynamic range of the amplitude is from 1 to 3, so you can see something like that. So now I will going to do some sort of discretization. And I will say that, okay, I will discretize this using 4-level discretizer. So what do you mean by 4-level discretizer? It's very simple. That you will limit your values to be 0, 1, 2, 3. These are the only acceptable values on the y-axis. What is in between will be either shift down or up, depending on the implementation of the discretizer. So in order to perform this here, what you are going to do is something like that. Okay, so you will say, okay, let's, for example, assume that you will round up and down based on the how much is near to the lower level or to the upper level. So, for example, you will have something like that. For example, as you can see now, this red signal is a discretized signal because it accepts only, actually, by the way, here we did not use 0 because the band of the energy of the signal does not include 0, but generally you use only discrete levels. This is the difference between the red curve and the blue curve. The blue curve is an analog curve that accepts any value between 1 and 3. However, the red curve accepts only 1, 2, or 3. You will never find any other values, only 3 values, in addition to the 0, which is unused here. So this is, the red one is what's called the quantized signal. So the quantization, as you can see, is the process of discretizing the y-axis value to a certain values. Later on, we can convert this into a code. Actually, this is somehow a future step, but let's do it, by the way. So by limiting to this 4 values, you can simply say that, okay, I have a 4 values, or I have, sorry, a 4 level. So this is a 4-level quantizer. Then, very simple, what you can do, you can say, in order to perform a 4-level quantizer, in order to digitalize, or what we call to encode this 4-level quantizer, I need 2 bits, because 2 power n is equals to 4. So as general, 2 power n is equals to what we can call L. In some other texts, by the way, it's called M. So L and M are both here. This is the level of quantizer, and this is the number of bits. So, for example, here you can say that okay, I need just 2 bits. This is 0, 0, 0, 1, 1, 0, and 1, 1. Whenever you would like to transfer this signal into a complete digital signal, then what you are going to do is simply you are going to represent this data. So this is 0, 1, and then 1, 0, and then 1, 1, and then 1, 0, and then 0, 1, and then 1, 0, and then 0, 1. So this simply represents the encoding of this data. Now you convert this data to be a complete digital data. This is what's called encoding. Okay, this is generally the process. However, we have to consider a very, very important and critical step here while we are considering quantization in R, is that the error due to the quantizer is unrecoverable. Again, the error due to the quantizer is unrecoverable. I mean, whenever you have a signal here, and this is the level. So let's, for example, zoom in this part of the signal. As you can see, this is the blue signal is the original value. For example, this value, for example, is 1.5. For example, in order to do this quantization step, you decrease this value to be 1. The receiver will receive this red, which is 1. The receiver can never restore back the 1.5 because simply there is no information at the receiver to tell what is this one. Actually, this one is any value between 1 and 1.5 because we agree that between 1 and 1.5, I will round down the value to be 1. So basically, this one could be 1, 1.1, 1.2, 1.3, 1.4, 1.5, 1.45, 1.32, any something like that. So this quantization error is unrecoverable error. You can never restore it back in the receiver. As you can see that this is simply whenever you have, let's make it a new page better. So as you can see, whenever we have, this is our quantization levels. So if I assume that this width is called delta, where delta is the distance between each successive 2 levels, in our example, for example, in our previous example in theory, this delta is 1 volt, for example. Of course, this can be tuned based on the dynamic range of the message as well as the number of levels. So we can actually have an equation for delta if you would like so. So if you say that this is the V maximum and 0 is the V minimum, so it's V maximum minus V minimum over L. So delta equals V max minus V min over L. So in our example, we have 4 minus 0 over 4, which is the number of levels, so we have 1 volt. So you can write an equation to describe this as, or the distance, the distance between 2 successes. So what is the maximum error? Actually, the maximum error is very basically easy. So it's some sort of approximation problem. So if you have, for example, 1.3, then you will round it back to 1, round it down. If you have 1.6, you can round it back to 2. So here, for example, the error is 0.3. Here the error is 0.4. So what is the maximum error? The maximum error is basically 1.5. It will be rounded either to 1 or to 2. And in most cases, the error is 0.5, which is delta over 2. So the maximum quantization error is delta over 2. This is the maximum quantization. So as you can see here in this case, this is the maximum. So let me now return back to our presentation and see what is inside. Okay, so I believe now you can see my presentation slides. And let's also open the output. Okay, so this is two examples for the quantizers. One, what we call the mid thread and the mid rise. The mid rise, for example, here, as you can see, the rise is in the original. Here, the mid thread is there's a state in around 0. So this is just two implementation or two different types for the quantization steps. It depends on where you are considering your 0. So, for example, what we just do in the example is a mid thread, because this was our levels. We have 0, 1, 2, and 3. Another way, you can make your levels half, for example, half 1.5, 1.2, 1.5, 2.5, 3.5, and 4.5, or something like that. So you can make a state around 0, which is what's called a mid thread, or you can make a no state around 0. So 0 is a transition with what's called the mid rise. So this is just a two representation. So again, here this is the error. I just illustrating to you. So the maximum error is delta over 2, and by doing somehow sophisticated mathematical steps, I will not go into its details. You can find easily that this error, well, it tends to delta square over 12. I think, yeah, this is 0. So this is delta square over 12. This is the average error, because this is what's called the maximum error, but for the probability of maximum error is not 100%. So by doing some averaging, you can reach the average error is what's called the delta square over 12. Again, delta is the width of the step, which, as I mentioned, is equal to V maximum minus V minimum over L, where L is the number of levels. So finally, another equation that may be useful, and this is actually a new term that maybe will be described more and more later in our previous, our coming lectures, which called the SN, or the signal to noise ratio. This is a very, very, very important term. Usually in the digital communications, we are defining the systems in terms of the signal to noise ratio. Here, this signal to noise ratio is given by 2 to the power 2n, where again n is the number of bits used in order to describe the system, which equals, or which can be calculated from the information that 2 power n is equals to n. So this is two basic equations. We can use it from time to time while we dealing with quantizers. However, we are not requested to know that full revision. Of course, you can access it using Simon Hayek if you would like to. However, it's not a critical part in our course to know that step-by-step revision for these two equations. So this is generally what we can call the quantization error. Sorry, the quantization error and the simultaneization. Herein, we deal with what's called the uniform quantizer. We call it uniform quantizer because simply the distance between each two levels is equal. So as you can see, or for our example, for example, if the distance was 1 volt everywhere, and here, as you can see, it's a uniform quantizer. Sometimes, or in some communication system, we can use what's called a non-uniform quantizer. This is actually depend on the format of the signal. For example, here you can see that most of the signal here, if you are going to use a uniform quantizer, for example, you can see that all the signal will be quantized only to 2 levels, and other levels will not be used. And this is actually will not be a very good or a very appropriate system in order to study or in order to quantize the signal. So in this manner, or in this format, what we are going to do is to use what's called a non-uniform quantizer. So in this region where most of the signal is located, you are going to increase the number of levels. So I mean decrease delta or decrease the step between each two levels. And whenever the signal probability of existence is very low, like here, for example, you are going to increase this delta. So you are using what's called a non-uniform quantizer. Actually, you are not going to go into details more than that regarding the non-uniform quantizer. So it's just to know the idea, the idea of the quantization using a non-uniform quantizer. But again, it's not a part of our course to go into details in this one. Okay, so now let's turn to the last step, which is the encoding step. In order to go to the encoding step, let me first return back to my presentation. Sorry, to my whiteboard. Here, if you remember, my dear student, I illustrate quickly the process of quantization, the process of encoding, where I mentioned that the process is very simple. We just convert these levels into some binary representation based on the number of levels using this equation, that 2 power n equals to n. So, for example, if you have 16 levels, then you will need 4 bits. If you have 256, then you need 8, and so on. So now you have this presentation, or this what's called this formatting of bits. Now the question is, how I'm going to represent this from this. So for example, let's do an example. So for example, if you have an input stream of bits, which is, for example, 1 0 1 0 1 1 0 0 1, and you would like to represent these bits. So basically, the best, or not the best actually, the simplest way is using a high and low bits. So you can say that, okay, this is a high and this is a low. So whenever I'm going to represent this data, so I will make it something like that: 1 0 1 0. Of course, this duration is constant, to solve the TP or the triplet. So 1 1 0 0 1, and that. So this is basically the most simplest way in order to represent the binary representation. However, this is not the only way. So we have different techniques that can be used in order to represent this stream of bits. What these techniques used in order to represent this stream of bits, what we call line coding. So the line coding are the different coding used to represent a binary representation. I believe that you are, as a computer engineer, already maybe aware of some of them. So let's make a very brief discussion regarding these line coding techniques. Okay, so let's do it here. Okay, perfect. So just to operate my laser pointer. Okay, so here are some of these line coding techniques. We have what's called the unipolar non-return to zero, or the polar non-return to zero, or unipolar non-return to zero, or bipolar non-return to zero. We are going to discuss step by step this representation. So again, this is the most easiest one, which is the first one, which we call it the unipolar non-return to zero signaling or line coding. So it's unipolar. Let's start to focus on the names. So it's unipolar because you are using only the positive portion of the voltage. So it's 0 or high, let's say 5. So it's 0 5 volts. So it's a unipolar, and it's not returning to 0 because it's a complete 0 or a complete 1. The 0 is a complete 0, or the 1 is a complete 1, and so on. Okay, so this is the first. This is the first step. The second one is what's called the bipolar non-return to zero. So bipolar, polar non-return to zero. So bipolar or polar means have the same meaning. Non-return to zero again. So you have a complete 1 or a complete 0, but now you are using 5 and -5. So here you can use 5 and -5, and then you can illustrate the 0 by -5 and the 1 by 5 and so on. So as you can see here, this is a different representation you can use. So the third one is unipolar returns 0. This is very interesting, because in the 0 again you have, if you compare number 1 with number 3, so this is the same 0 bit. 0 is represented totally by 0. However, the 1 is represented by 50% 1 and 50% 0. So you decrease the duration of the 1 representation. So it's 50% 1 and 50% 0. Okay, finally, we have what's called, or not finally, actually, the third one is called the bipolar returns 0. So again, in the bipolar returns 0, you are representing 1 with the same like in the one above, so half percent 1, half percent 0. However, for the 0, you are making some sort of alternating. So the first 0 is represented as a 0. However, the first 0 is 0, 0 is 0 everywhere. I'm sorry, 0 is 0 everywhere. However, for the 1, the first one is represented with positive. The second one is represented with negative. So these, both of them are 1s, but the first one is represented with a positive voltage, while the second is represented with a negative voltage. And then the third one with a positive, and then the fourth one with a negative, and so on. So this is the fourth one. So now this is a representation, or what's called the bipolar return to 0. Finally, we have the split phase, or what's called the Manchester code. This is somehow very interesting. So for the 0, you start with the 0 and then you turn to 1. For the 1, you start with 1 and then you turn to 0, as you can see. So this is what's called the Manchester coding. So as you can see, it's just a different representation in order to represent 0 signal. Now, my bonus question is, why are we investigating time in order to have different line coding? Maybe what comes to your mind is why we should fix every digital signal to be in this format, which is a normal and logical format. Why we should go into more and more investigations in that format? The answer is in the frequency domain. If you remember, my dear student, one of our previous very early slides here, which actually I skipped somehow quickly, whenever we talk about the advantages and the disadvantages of digital communication system. And I told you that one of the advantages was called the noise immunity, and we already discussed the noise immunity in the end of lecture number 4, while we are considering the difference between, or the advantages and disadvantages of FM and AM modulation. And I told you that, please trust me, that the noise immunity for digital communication is much better than analog communication. Maybe we will come to this later on while we are dealing with digital modulation techniques. However, we say that we have already a disadvantage, which is the more bandwidth requirement. You can easily recognize it, because whenever you are dealing with a digital modulation signal, or whenever you are dealing with a digital signal, you should expect sharp edges. And as we already discussed together, sharp edges mean high frequency components. So basically, without going into very deep analysis, we will do this deep analysis, but before going into this deep analysis, we can easily expect or forecast that the bandwidth requirement for the digital signal, digital modulations, will be much lower than the analog modulation, due to the need of representing the signal in a form of a sharp edges. So, okay, again, then sharp edges everywhere. All these 5 techniques include sharp edges. But what is the difference between the frequency spectrum of this signal? So this is your term. I will leave this for you. Please use your knowledge in Fourier transform and use actually your knowledge on also in the Fourier transform properties in order to investigate from your perspective what is the difference between the frequency spectrum of such line coding. So please investigate. Of course, this piece of information can be easily can be easily captured from any literature, or maybe if using Google or Wikipedia or whatever. So please go on and Google it, no worries. What I'm seeking for is not that you invented from scratch. What I'm seeking for is that you understand and illustrate what you understand. So please go search and try to investigate what is the different philosophy or what is the different perspective of different line coding techniques. And usually, please, this is my advice, maybe my hint to solve. Usually think about the two main parameters, power and bandwidth. These two main parameters are the main parameters that affecting the communication system, the bandwidth and the power. So start to investigate the difference between these line coding techniques, using in your background what is the difference in power needed, what is the difference in bandwidth requirement needed for these different things. This is the end for our lecture number 5, which deals with analog to digital transformation or analog to digital conversion. In this lecture, you should now understand the concepts of sampling, sampling, quantizing, and encoding. In the next lecture, we will continue in the block diagram of the digital modulation. Now we have passed the first block diagram, which is the analog to digital conversion. In the next stage, we will going to deal with different digital modulation techniques. Actually, we are going to spend something like 2 to 3 weeks in order to investigate different modulation techniques. I mean, digital modulation techniques. And also in order to make some sort of comparison between analog modulation and digital modulation in terms of bandwidth, energy requirements or power requirements, noise immunity, and all this stuff. This is a termination of chapter number 5 or lecture number 5. Thank you very much for your concentration and see you inshallah in the next week. Thank you.